when I was younger, I couldn't afford an A86, and one of the guys in my neighbourhood had a KE70 which had a 4AG in it, and it was a mad little car. The amount of torture that he gave that thing was abnormal, and it just copped every bit of it. So I just fell in love with it. The 4AG obviously naturally became the engine that you wanted in that car, and then obviously you look into the Formula Atlantic as being the pinnacle of the 4AG world.
Welcome to the HPA Tuned In podcast. I'm Andre, your host, and in this episode we're joined by Matt from MT Engines in Australia. Matt specialises in building Toyota 4AGEs of all different varieties, and this is an engine that holds a near and dear place in my own heart. One of my early cars was a DX Corolla KE70, and we'd gone through a few iterations of engines, but ultimately it ended up with a 4AGZE bottom end, a silver top 20 valve head and a turbocharger, and it was a huge amount of fun. I've built and tuned all manner of 4AGEs over the years, but I'm definitely not the expert on the field that Matt is. So it was really interesting to dive into this conversation with Matt and learn what makes the 4AGE what it is. Most importantly, how do we get more power out of the 4AGE? And of course, the mythical Formula Atlantic version of the 4AGE that anyone who's owned one of these engines probably has aspired to build or own. We find out what actually went into these engines, why they were able to make so much power, and just as importantly, what it would actually be like living with one on the day-to-day in terms of maintenance, drivability, and all of those other things that are easy to forget about when you're just looking at a spec sheet of power and torque. Now, you're probably getting the idea that this conversation is going to be very 4AGE centric, and yes, it absolutely is. But if you don't have any interest in this particular engine, don't worry, there's still a lot of generic information in this podcast that you're going to be able to take away. Before we get into our chat with Matt, for those who are fresh to the HPA Tuned In podcast, High Performance Academy is an online training school. We specialize in teaching people how to build performance engines, how to tune engines, how to construct wiring harnesses. We also cover topics on race driver education, race car setup, data analysis, and even fabrication. All of our courses are delivered via high definition online video modules that you can watch from anywhere in the world, provided you've got an internet connection. If you want to learn more about our courses, you can head to hpacademy.com/courses. There's a full list of our courses there. You can also use the coupon code podcast75, and that'll get you $75 off the purchase of your very first HPA course. I'll put a link in the description to that coupon code as well as our courses page. All right, enough of our introduction. Let's get into our chat with Matt now. All right, welcome to the podcast, Matt. Thanks for joining us. And as we always do, let's start by finding out a little bit about your background and specifically how you got into the automotive industry.
Yeah, so I left high school and started working at a electrics place that we were doing electronic pool equipment. And my mum begged me to get a trade, so I moved into engine reconditioning. I was taken under the wing by a man named Adam Moore, and he owned a company called LW Parry Engineering with his father. So engine reconditioning, fitting, machining, and yeah, I basically got taken under his wing, and he was into car racing. He actually had a Clubman, which he used to race, and it had a 4A, 7A stroker, which was a 2-litre, and he was racing this like over 20 years ago. So very early on, he was doing the 7A strokers, and he was making about 240, 250 naturally aspirated on these engines at about 8,500 RPM. So pretty good power and torque for a 1.950cc 4A.
It's also an engine that's quite dated by modern technology standards as well.
Yeah. But he shared a passion for 4As like I did, and I was in fitting machining there with LW Parry for about 4 years before they decided to close the business down. Then I was taken into Maatouk's racing. They sort of needed someone who could machine, didn't know anyone, and our business was closing down. So a friend of mine, Rob Arbolino, who was working for Maatouk's, basically said, Anthony, we need to get this guy in, buy the machinery and get him working so we can keep up with demand for building engines. So I used my experience, aspirated horsepower, combine that with what we were doing at Maatouk's with turbocharging. And yeah, we were turbocharging RBs and basically just at the time taking down records left, right and centre.
So it sounds like you've really got experience at both ends of the spectrum, sort of 4A engines, great little engines, and we're going to dive into them in a lot more detail as we go, but certainly not going to set any world records for power, and then obviously the big turbo massive power RBs, which absolutely are. I want to come back a step though, just talking about getting this trade under your belt. You said your mum was basically begging you to do that, and in terms of becoming an engine reconditioner, what does that process look like? You said you worked at that place for 4 years before they sort of shut the doors. How long of that 4 years was getting your trade, and what does a trade even entail in Australia?
So in Australia, the trade background is generally about 3 years. So of carpenter, electrician, it's about 3 years going to TAFE, which is a college for learning. And you do that about 1 day a week, every week for the first 3 years. And on the fourth year, you spend 1 full year in that industry. And then generally you get signed off as a tradesman. Sometimes there'll be a test. An electrician needs to do the capstone, which is a test. They pass that, they become an electrician, they get a license. For an engine reconditioner, basically your boss at the fourth year would sign off, send the paperwork down to, the college or the government, and then they would send you back a trade certificate to say that you're qualified in this industry.
Okay. In terms of my own experience with engine reconditioners or engine reconditioning shops that I've dealt with, because my own engine building, I don't have a machine shop, so obviously we become reliant on outworking that element. But where I'm going with this is the quality of results that I see from engine reconditioning shops are quite variable. And I've always put this down to the fact that I think probably it's safe to say 95% of engine reconditioning shops deal with your average garden variety street car, probably mostly naturally aspirated, very low specific power levels, low RPM range. And what this means is therefore the attention to detail, I guess, and the clearances, the tolerances are not quite as critical as they are in a 2,000 horsepower RB or a 200 horsepower 4A for that matter. And I think, again, I'm reading between the lines here. It's not an industry I've directly gone through and done my own trade cert, but I kind of feel like in a lot of people that maybe breeds a little bit of complacency and a she'll be right mentality. Am I right here or am I missing something?
The shop that I work for, we specialised in very small engines down to lawnmowers and whippersnippers, piston size. We used to do Briggs and Stratton motors for junior dragsters, and then we would go all the way up to V16 locomotives with 4 turbos on them, 38 litres plus. So these engines were the size of cars. So we'd done such a variety of things. We used to do a lot of restoration stuff too. I can actually white metal bearings, so I can actually make bearings from scratch. One of the guys that I worked with was from South Africa. He used to do white metal bearings for vintage restorations. So we used to do a lot of vintage restoration engines. So I got to learn such a broad variety of stuff. And everyone particularly that I worked with in that facility really cared. They actually cared. So quality and attention to detail was very, very high standard. And then after leaving that industry and then utilizing other machinists, sometimes you almost have to risk sending out an engine block to a workshop, getting them to do some work on it, and then you get it back and they've essentially ruined it so you have to be prepared to trial and error because, like you say, that attention to detail or care isn't there.
Yeah, and I mean, I don't want to, obviously we're probably going to have a bunch of mechanics and engine machinists listening to this and shaking their heads right now, and I'll probably be getting death threats in the morning. I'm not trying to say that this is across the industry. Obviously, there's some great operators out there turning out super high quality work, but I mean, unfortunately, I think it's just that's maybe not the norm in that industry, which kind of brings me back to another related question. You kind of just touched on it anyway, but with our own engine building courses, one of the common questions we get, and we try and deal with this in the course as well, is, okay, cool, I want to build my own engine at home. I'm going to have to deal with an engine machinist. How do I choose one that's going to actually give me good work? Now, you just mentioned, you can sort of send out a block as a bit of a test, and sometimes it's going to come back ruined. I mean, obviously, we don't want to do that if we can avoid it. That gets pretty expensive and soul destroying for that matter. Are there any other kind of tips that you can give our listeners on how to sort of sort out the good from the bad in the engine machining world?
Look, I think maybe doing like one of your courses where you get taught how to use measuring equipment and taught how to identify what you're actually trying to achieve would be one of the big ones. I mean, you could walk into some of these machine shops and just ask them to see their work and then go out the back of the workshop if they're happy to show you, and then basically just look at the quality of work they're doing, look at the facility that they're working in, their attention to detail in their day job. I mean, if you're going to go spend money with these guys, you really sort of want to know that they're actually doing the right job for you. One of the things I do for my customers when I build engines is I film everything, photos of absolutely everything from the process, because one of the things at the end of the day is if I assemble an engine and I've told you I've put all these parts into it and charged you all this money, how do you know for a fact that those parts are in that engine? So one of the things, yeah, like you say, is just photographs and video evidence. It's really easy to do, and it gives the customer sort of this, like, look how clean this thing is. Like, it's almost as a piece of art. You don't really want to start it up and run it in a car sometimes.
A little story that just popped into my mind as you were saying that about not knowing what's inside the engine and just taking for granted that it's actually what you paid for. I mean, obviously, you're dealing with someone who's got some integrity. That's going to be the case. But unfortunately, this industry is a bit checkered. So back when I was running my old tuning shop, I had a customer who had a Skyline, R32 Skyline with a build RB30. And I'd been sort of involved in the tuning of that from when he brought the car to us. It was a previously built engine, no real backstory on it. And it always had a really weird vibration to it. And we chased this for a couple of years while the customer owned it. And it only happened at a certain RPM range, but that happened to be quite noticeable at sort of a low-speed cruise. And we went to the point of having the flywheel and clutch removed and checked and rebalanced, and that made no improvement. The front pulley was replaced, all of the sort of normal stuff you did. And we got nowhere with it. And anyway, I think after about 3 years, the engine suffered some kind of failure. I can't remember exactly what it was, but it gave us the opportunity to open it up. And the reason it had a vibration is that it had 5 rods of one brand and one completely different random rod that weighed something in the region of about 15 or 20 grams more than the others. And you sort of look at this and you're like, you could not make this shit up, honestly.
That's amazing.
So that's the bad side of things. Unfortunately, some people will do whatever they need to do to get through and deliver the customer a subpar engine. And obviously, we don't want to be dealing with those sorts of people where possible. Well, what I'd say is a couple of things to go towards like, how do we choose a machine shop. I think everything you just mentioned there's a really sound place to get started. Looking at a machine shop that at least has some experience with the type of engines you're dealing with and ones that deal with race engines. That would probably be my key. I've always suggested a really good place to start would be talking to people in local car clubs and seeing who the car club members are actually using to build engines or machine engines, because word spreads pretty quickly, and if they're dealing with a machine shop that's no good, you're going to hear about that very, very quickly. One element that I find quite hard to sort of pin down is the quality of the machining equipment and how clean the workshop is. And the reason, these are sort of two separate elements. I have dealt with machine shops over the years where there's engines stacked floor to ceiling, the place is in absolute shambles to look at, and you sort of shake your head walking around thinking this is just a health and safety violation waiting to happen. But they turn out some impeccable work. So it's one of those, I can't always judge the book by its cover in that regard. And then on the same note, these days, modern machining equipment is almost always going to be CNC based, and the precision that can offer, the repeatability, I totally get it. But there's also some of the older operators who have been using manual equipment for decades. They know it inside and out, and they can turn out amazing work with this manual equipment. So what's your take on the quality of the equipment versus the skill of the operator on the equipment? What's the most important factor?
I think maintenance of the equipment is probably one of the big ones. One of the things, like just as an example, I've seen a milling machine that mills blocks or cylinder heads, and if you're machining, say, like a 4-cylinder head, which might be, say, 50 centimeters long or 30 centimeters long, and if you're only machining a lot of 4-cylinder heads and the head is mounted in the center of that travel bed, you generally find that the machine actually starts to get some wear just in the range that it uses, a good machinist will actually run the whole length of the bed and run the mill cut, even though it's not cutting the cylinder head, run the entire length of the bed for every cut. And although it takes longer, you'll find that it won't wear the bed right where the machining task is happening on that 4-cylinder head. And you could be talking V8 cylinder head, which is essentially a 4-cylinder head length, a 6-cylinder head, and then obviously then you've got space on either side of that cylinder head. So things like that, a good machinist, you'll see them run the entire length of the bed because they know in 10 years' time the machine's still going to have the same amount of bedway wear along the whole travel.
Yeah. Okay, that makes sense. So obviously not something I would have thought of, not being an engine machinist, but that's why I think it's so important. It's the machinery is one element, but it's the case of the operator that knows how to get the best out of that equipment, and in this point here, how to make sure it's still going to do a great job in another 10 years' time as well. Let's come back full circle to getting into engine machining. And at that point, you could have chosen a number of fields within the automotive industry. What was it about building engines that really stood out to you?
Engines just seem to fascinate me over like the general mechanics of a vehicle. I mean, it's hard to say, is a mechanic just a parts fitter, or are they repairing just say, the clutches and diffs and like you've got these individual tasks. Like there is a diff shop that specializes in differentials. You've got manual gearbox transmission specialists, automatic transmission specialists, and engine specialists. Is the mechanic the guy that just puts all that together? And then within these specialist trades, you've got like this, highly skilled workforce of guys that, specialize in that component, compared to then the mechanic who puts it all together. I didn't want to be the guy that put it together. I wanted to be the guy that fixed the engine, because I knew that I could also be the guy that puts it together. That's, I guess, an easier task in saying that. Like the machinist is generally the guy that's the diff guy. He's also the manual gearbox guy, and he's also the engine guy. But to become a mechanic I didn't see that as hard, I guess. I wanted something that was going to be more difficult.
Yeah, okay, that's fair. And it absolutely is. I think that's reasonable to say. In terms of other areas as well, I've always found, at least from my personal standpoint, that engine building and engine tuning, there's a lot of crossover there, which is why I sort of specialised in doing both of those myself. Is the engine tuning something that you've also got involved with?
Oh, yeah. So I'm an engine calibrator as well, because, I mean, I don't know if this had been your experience growing up, but I was building my own engines as a kid, and I was relying on other tuners to tune them. And I was going to tuners, and I just was paying too much to get a bad result. They were making mistakes, and I just thought, this can't be that hard. So I ended up actually getting injured snowboarding and broke my spine. So I was bedridden for a little while. And whilst I was in bed, I decided, hey, might as well use my time sitting here in bed. So I actually started reading the Maatouk manuals, the Adaptronic manuals, every manual for every ECU that was available out at the time. And surprisingly, the amount of information that you get from that, plus my mentor, I called him and was bombarding him with questions. How does this work? Like, how does the timing gun work to this? And how do how does that correspond with the ECU? And he was also tuning his own engines. And I've listened to one other podcast talk about the old Maatouk M4. And funnily enough, that was the first ECU I tuned. And wow, how far has ECU technology come since that?
Yeah, I must admit I haven't dealt with an old Maatouk M4 for a number of years, and they're a bit of a blast from the past when you do dive into them. But I mean, hats off to Maatouk, they still do a great job. In terms of putting your sort of book knowledge, I guess, with tuning into real world practice, how did that sort of pan out? How did you get proficient at actually pushing the keys on the keyboard and making sure that you're pushing the right keys?
I had a lot of good help. I had a lot of guys steer me in the right direction, good mentors. Basically, one of the guys that I was asking questions said, hey, if you want to tune, don't be scared. Give it a try. And he goes, I've got these knock ears here. And he goes, here, take these knock ears and then go have a listen and just drive your car around and just tinker. Like, play with your wideband, play with your ignition timing. And we're talking about naturally aspirated 4As. I mean, they're pretty resilient.
Pretty hard to break.
Yeah. So it was just really just trial and error for me. And this was, I don't know how long ago, this was a long time ago. And I just don't think there was no real fear because I was an engine machinist and builder. So if I broke the engine, it's like, well, I've got another few spare here, I'll just build another one. So, and although I never broke an engine, there was no reason for me to be scared of it. So I just tried. And yeah, I guess that's not a lot of people don't have that opportunity. So if they break an engine, it's catastrophic. Like, there's a lot of dollars involved.
Yeah, I think there's this misconception, though, that in order to become a proficient engine calibrator or tuner, you have to break some engines. I hear that said so many times, and my personal opinion is it's absolutely completely inaccurate. You should not be breaking engines, with some exceptions. I mean, I was involved with drag racing where I had customers that wanted to break world records, and we absolutely did that. And sure, if you're taking an engine and you're trying to put out 4 or 5 times the factory power and maybe rev it to 10 or 11,000 RPM, you're at the absolute knife edge of everything has to be working right. The stars have to align properly to get good reliability out of those engines. Yes, under those circumstances, some failures are going to happen. That's kind of the risk we sign up for to build engines at that level. But with your sort of normal, slightly to moderately modified engines, I mean, if you understand what sort of air-fuel ratio targets you should be aiming for, you understand knock or forms of abnormal combustion, and you have ways to monitor it, as you mentioned, knock is, and you stay away from knock, you should not be breaking engines. That's my strong opinion, unless something random goes wrong that's sort of outside of your control. And I think this is kind of the expectation that a lot of dodgy tuners have built up in the aftermarket industry is, I'm going to take my car to a tuner and there's a better than average chance it's going to come back broken, and I accept that. And that just shouldn't be the case in my opinion anyway.
What you've just said there, one of the things that I get asked a lot to do is, I want an engine that makes, let's just say, 1,000 horsepower, and I want it reliable. And I'm like, those two words do not go together. It's 1,000 horsepower out of, say, an RB6 cylinder or whatever engine you want, a 4G63 or an SR20, and reliable, they don't go together. These engines were never meant to designed to be pushed to this level of power. So what is your definition of reliability? And it's just, that doesn't work.
I think it comes down to expectations and unrealistic expectations that sadly are formed by the internet, because any car magazine or any car blog site that's got articles on the sort of cars that we're interested in looking at, cool cars that make a lot of power, just about everything these days has 600, 800 or 1,000 horsepower. So people are preconditioned to these numbers that they throw around. It's easy. But the reality, the backstory behind some of these car articles, you don't get to understand how little or often the car's being driven, how many kilometres it's doing between rebuilds, what is actually required in terms of maintenance. Those factors, they're not interesting or sexy, so they get left off. And when you actually dive into reality, as you say, I mean, 1,000 horsepower RB absolutely can do it, no problem at all. It's a pretty well-known recipe and it's not that difficult. But is it going to do 100,000 kilometres between freshen ups? Absolutely not, particularly if you're going to drive it the way it's designed to be driven. And that's the element, I think, setting that expectation with a customer as to what is realistic, what the upkeep and maintenance is going to be, and what the cost is going to be. All of those factors need to be dealt with in order to, so we're all going in the same direction and we're on this journey and we know what we're up for. I think that's really important. Would you agree?
Definitely. 100%. Yeah.
Let's come back to the little 4A, because it is one of my favourite engines, and I'm going to pick your brains on this throughout this podcast because I've got a project in mind which may come up a little bit later down the track, which will involve a 4A. So I'm pretty keen to sort of see what I can learn from you. For a start, why the 4A, 4AGE? Why did you sort of embrace that as an engine that you've got a particular passion for?
Two main aspects. One was a cartoon called Initial D. I'm sure everyone's heard of that. And when I was younger, I couldn't afford an A86. And one of the guys in my neighbourhood had a KE70, which had a 4AG in it. And it was a mad little car. The amount of torture that he gave that thing was abnormal, and it just copped every bit of it. So I fell in love with the design of the shape of the car. Although they're a square box, essentially, they're basically a brick on wheels. I just fell in love with it. So the 4AG obviously naturally became the engine that you wanted in that car, because in Australia, some of them, they didn't come with the 4AG, the fuel-injected version. So that was the engine. And then obviously you look into the Formula Atlantic as being the pinnacle of the 4AG world. Then obviously in Initial D, they had the Group A 20 valve, which was like, also that's like the epitome of, where you want to be in the 4AGE world.
There's definitely a lot of recipes in terms of 4A parts swapping between different bits from the Toyota parts bin, and it is a very easy engine to make moderate power out of. Probably a much more difficult engine to make really high power levels, and I'm talking this sort of Formula Atlantic spec, which I'll dive into as well. In terms of the backstory of the 4A design, I had in the back of my mind, and I can't remember where this information came from, that this was actually based around the Ford BDA Cosworth engine. Toyota sort of, I guess, essentially copying what worked for Ford. Is that correct, or is that sort of urban myth?
If you actually get a Ford BDA head gasket and lay it over a 4AGE, you'll be very surprised how everything lines up. Bore spacing, bores, head bolt holes, everything pretty much.
So Toyota just took that and added the sort of Japanese engineering and reliability potentially to it.
I won't say that Toyota stole the design, but yeah, pretty much.
Okay. Now, in terms of the 4A family, this is, again, quite vast, and this probably could get quite deep pretty quickly for those who maybe aren't super into 4AGE engines. But let's look at that holy grail, the Formula Atlantic engine. So this was used in a race series, Formula Atlantic, obviously. If my memory serves correct, the best of these engines were supposedly around about the 240 horsepower mark, and I think revved to sort of 10,500 RPM or thereabout. Are my numbers about right?
Yes, that's correct. So 250 horsepower was the good ones. The real top of the end, top of the line, Hasselgren and Leunings engines were doing about 250 flywheel horsepower. So these were all engine dynoed, and like you say, about 10,500 RPM was the top RPM on those engines.
When I was a little bit younger and sort of forming a bit of a passion for cars, I think my background sort of sound a little similar to you in terms of the cars you're involved with. I had a K70 of my own, and that ended up running a variety of engine combinations, but I settled on a 4A GZE, the supercharged bottom end with a silver top 20 valve head, and actually had a hand-me-down turbo from my old drag car, my Evo. So that was my daily driver for a number of years, and it was a huge amount of fun. We ended up with about 500 wheel horsepower out of that car, which is insane considering it was, for all intents and purposes, all stock internal components on the engine. But like a lot of people, I sort of looked to that Formula Atlantic holy grail and kind of aspired to build something of that nature. What is the recipe for getting 240, 250 horsepower naturally aspirated out of a 4A?
So realistically, it comes down to a few aspects. One of them is compression ratio, camshaft profile, duration and lift, and port design and valve design. Pretty much, if you get that combination right, obviously intake runner length and diameter and exhaust runner length and diameter.
So everything.
pretty much everything. Okay, yeah. So
yeah, I mean, you say all of those things individually. Sounds pretty easy, but I mean, there's levels to each of those elements, and I mean, this is kind of the thing I find. Building a high-powered turbocharged engine super satisfying because it is easy to make really big numbers. I mean, there's a lot that goes into it, but for all intents and purposes, if we want more power, we choose the right size turbocharger and run sufficient boost. And if the engine mechanically can hold together, we're going to end up with some big numbers. Naturally aspirated engines, you can't really hit them with that sledgehammer approach. They are complex and they're sort of very finely tuned, and every element has to work together, and if you don't get that combination right, you can end up with a bunch of expensive parts that just don't work together, correct?
100%. So luckily, I guess for us, the roadmap is already in place to build these engines. So if you look at, say, what Hasselgren or Leunings are doing, the exhaust runner lengths, it's all there, diameters, tubes, the intakes, so the TRD intakes, like the intake manifolds and throttle bodies, that's all there. Obviously, some of the things that you have to do yourself are like, say, your port design. And the difference between Leunings and Hasselgren will vary very, very slightly. But realistically, these guys are running big port heads, ported out, CNC ported out. They've got quite a funny shape design, actually. And, then obviously fitting the biggest valves they can in them. So the engine that I just had here recently, a Formula Atlantic engine, which we turbocharged, that had 4 mil oversized valves in it from standard. So
wow,
absolutely massive. So mind you, the factory valve seats can't cope. So it had beryllium oversized seats. But yeah.
So, I mean, obviously, for a lot of the popular engines, we can generally buy from a few suppliers, maybe Fourier, Supertech, etc., off the shelf 1 millimeter oversized valves. And within reason, not maybe every engine, you can usually machine the existing valve seats to take that 1 millimeter oversize. But what you're saying there, if we go 4, that's massive. So then it's a really big operation, machine out the existing valve seats and fit in new custom valve seats into the head and then machine those, correct?
Correct, yeah.
Okay. In terms of the other bits, you sort of just insinuated that for an Atlantic build, a lot of this stuff is off the shelf in terms of, you mentioned the inlet manifold. I assume back in the day that was potentially maybe a control part. What about aspects such as the camshafts, the pistons, the rods, etc.? Are these all sort of a control part, or is each of the engine builders kind of using their own combination and having custom parts built?
So I believe that in my experience with what I know, the TRD crankshafts were actually made by Marine Crankshafts in the United States. So they're a custom crankshaft manufacturer. And TRD USA basically got them to make the crankshafts for them. The camshafts were actually a TRD unit. I don't know if they were made in-house by Toyota, but the TRD camshafts for the former Atlantics, I'm assuming, and I can't say this for certain, were made in the US. And these guys were over 300 degrees of duration and like 14 mils plus of lift. Like, they were absolute monsters.
I guess where I'm going with that specific question was the freedom to try different cam profiles and tweak that, or is this like everyone is running essentially that same TRD cam?
I'm assuming that everyone ran the same camshaft because they were running them to about 10,000, 10,500, and to achieve that sort of the power level to that RPM, you sort of need that sort of duration. In my opinion, you probably could have pulled a little bit of cam out of them and then probably pulled a little bit of valve spring out of them too to try and make more power and not have the engines fail as soon. But I guess back in the day when they were running that series, they didn't have spintrons, and a spintron is a pretty good tool.
Yeah, we're talking about quite a long time ago, and the fact that people still talk about the Formula Atlantic engine, it really was quite an achievement. You've just mentioned spintron, so let's dive into that. What is a spintron, and how does that help when you're designing engine components or valve train components?
So a spintron's a machine which is basically a big DC engine that bolts to the back of the engine. You basically run no spark plugs and no cam covers on the engine, or clear cam covers. And using lasers, it actually measures your valve deflection. So the DC engine will spin the engine over and run it up through the RPM, and lasers will actually measure the actuation of your valves, and then basically the spintron is then measuring to see if you get valve float through the RPM range. So realistically, if you had a spintron, you could develop like camshaft profiles and you could start dropping spring pressure out of these engines, because you've got to understand that if you're running such high spring pressures, the engine physically has to operate that. So you're losing torque from the engine to operate your valve train. So you want to try and run as minimal spring pressure as possible, but at the same time have enough to keep the engine in operation. So spintron's a really, really good tool to measure that and pull valve spring out of it. So if they had that back in the day, I mean, one team could honestly dominate, because they could start pulling spring out of it, pulling cam out of it if it was unnecessary to make the same power, because you'd just move between the spintron and then the engine dyno and just keep testing.
Yeah, absolutely. In terms of the cam profile as well, and just saying we've got X degrees of duration and so many millimeters of lift, there's, at least my understanding, I don't grind cam profiles, but I've talked to a few people who are deep in that sort of area. There's sort of, you could have two cam profiles that on paper basically deliver the same net result, lift and duration, but you could have one, the design, maybe I guess it might be the way the valve is ramped up off its seat, and then at the other side, as it's closed back down to onto its seat, that tends to beat up on the valve train much more harshly than another cam profile. Is that an issue as well? Is that again an area where the spintron can be used to sort of help with that development, or does that go a little bit deeper?
Yeah, definitely. So I've been looking into Billy Godbold, I think his name is, at Comp Cams, and he's been doing some really cool stuff with the spintron at Comp Cams. Although they're dealing with like LSs and V8s and things, it's really good to know what's going on in the industry outside of my small world of Toyota 4As. So looking at the spintron and what they're doing with cam profiles and what they're able to actually achieve, I still think there's so much more that we can do in development when it comes to the cam profiles that we're working with. I mean, also you've got other aspects like the weight of the valve train and beryllium copper seats, which act like a sponge. They sort of absorb the impact of the valve returning to the seat, so you can have these more aggressive profiles. But is it necessary to have that profile with, a better shaped lobe? I mean, if you can optimize out of the shape of the lobe, then you can drop spring pressure out and make more power and torque.
Now, another element that's really critical to developing power in a naturally aspirated engine is the compression ratio. And to a degree, more is better. This comes down to the octane of the fuel available as well, because if we can't achieve MBT timing, we're knock limited. Well, chances are we either need a better fuel or we've gone too far with the compression ratio. But we sort of also can get to a point where to get what could be theoretically the ideal compression ratio, we end up with this massive dome on the piston, which actually is a negative for the flame front propagation. It's kind of sitting in the way. So can you give us any feedback on balancing those two elements, getting the ideal compression ratio without actually negatively impacting the combustion process?
So you're exactly right. When people talk about compression ratio, and this is one of the things that I've sort of always really found really, really interesting, is they consider their static compression ratio, but not their dynamic compression ratio. And I don't know if you've used that term before, or like when you start increasing the cam duration and profile, when you start reaching overlap, you've got this sort of, you start to bleed off compression as it's sort of on overlap through the passage between the inlet and exhaust valves as it's cranking over. This is really, really good for scavenge. But like you say, then coming back to static compression ratio, yeah, definitely a more flat style piston with no sharp edges on it, and then trying to maybe machine the head down as far as possible to try and get that compression ratio up without actually having the piston doing the work for you.
So you want less combustion chamber capacity or volume as opposed to increasing the dome capacity.
That's one of the things I've found. But then also you start to destroy cam and crank timing because you're moving the cylinder head so much further down by machining it. So you then, obviously, it starts to become a thing where you might have to slip teeth on the cam gears, degree those in, dial those in. And then obviously your cam profile, your cam cards that come with your camshafts, they generally get you in the ballpark, but you'll find once you hit the dyno that every single engine is different and it's going to require something else to make MBT or, maximum power torque.
Now, I mean, you've just really highlighted the fact that there's a lot of factors that go into this, but I mean, could you give us a bit of a guide for a naturally aspirated 4A that you're building? And I'm not talking here Atlantic spec, a good solid performer that's going to run on just a pump fuel, like a good octane pump fuel, so nothing exotic. What sort of compression ratio range would you say is sort of feasible for that kind of engine combination?
I'd be doing at least 11.5 to 1 compression static, and I'd be doing at least a 272 degree camshaft. And just a bit of a plug there for Kelford. You New Zealand guys, kill it. Kelfords are really, really good, always got stock, really cool shit.
They do produce a good quality cam, I can attest to that. We've run those in just about everything we've ever built, and it's nice to have a New Zealand company that's actually crushing it on the world stage with their cams as well. So yeah, another free plug for Kelford. There we go. Now, coming back to the Atlantic engines, again, like as I mentioned, the holy grail, and everyone who was into those 4AGE engines kind of aspired to build something like that. And this kind of comes back to the whole getting your expectations aligned correctly. When you're taking these little capacity engines and spinning them to 10,500 RPM, making 240, 250 horsepower, what's the sort of lifespan on one of those engines between overhauls or rebuilds, freshen ups?
10 hours.
10 hours, okay. Yeah, that's not a lot. It's not a lot.
This is the kicker though. 10 hours wide open throttle. So generally these engines were running the Cosworth Pectel ECUs. You couldn't put any other ECU on it, but basically 10 hours at wide open throttle. So because they're in a Formula car, generally they are at wide open throttle all the time. That's out of the corner, wide open throttle. They're off the throttle only for cornering. So in an event, you might only get an hour or something out of it in a full event. So basically you get about 12 months of racing out of these cars, depending on how many races you've got in the season. But 10 hours is basically where you start houring out, and that's a term where the components hours, life in hours, houred out, you just throw them in the bin and replace them. So you would hour out your valves, springs, like buckets, Most of the components really just get hourred out very quickly. And then obviously you can crack test rods, crack test the rod bolts, replace pistons. If there's damage to the pistons, change those. If they're still measuring okay, we'll put them back in, send them around again.
So this kind of comes down to a bit more of a subjective look at the component and sort of inspecting them for any potential downsides. And if they check out fine, at least the rotating assembly, the bottom end, could go another turn.
For sure.
A little bit harder with the valve train though. There's not sort of so many tests we can do that are going to definitively say if this valve spring or valve is on its last legs.
One of the things that I do with the valve train is I record every single one of my lash settings, and I monitor that. Even on my customer engines, every single customer engine that I do has a serial number on it, and that goes into a book of mine, little leatherback book. And what happens is I measure those, and if there's any variation for those over time and they start to lose valve lash, what's happening is the valve's actually starting to cup. So the face is actually starting to buckle and the valve stem is actually starting to protrude back into the cylinder head, and you start losing valve lash. So if I ever start to see valve lash loss, I'll record that and then monitor it. And if it starts getting below a tolerance threshold that I say is acceptable, then we've got an issue. So then let's just say I've got a solid bucket conversion on a 4A, so it has no shim, completely shimless. I will change out to give extra clearance, but if I see that move any further, pull the head off. We've got to start looking for an issue here, whether it be the lobe is running dry and it's slamming the valve against the seat. It could be tension between the valve and the valve guide. So if the valve, when you pull it out of the cylinder head, you might see like scoring on it from the actual bronze guide, if you're running a bronze guide, from it being too tight. And basically, as the valve's returning to the seat, it can get jammed momentarily and then slam shut. And then that can start cupping the valve over, especially if you're running high spring pressure.
Yeah, okay. I mean, it's these things, monitoring them and getting on top of them before they cause an issue is really the key here, because you have a valve let go and you're not going to have a lot that's going to be recoverable from that engine.
Yeah, it's catastrophic. If you're running a turbocharged car, you even lose your turbocharger, because when the valve head pops off, it goes out the exhaust port, straight in through the turbine wheel, and it's all over, and it just destroys everything. So monitoring valve train is probably the biggest thing for me, because generally bottom ends hold together pretty well. I mean, if you know the limits of what crankshaft, a rod, and a piston and gudgeon pin can cope with, and you keep it under the threshold of where you know that there's a failure point, then monitor your valve train a lot more closely than the bottom end. Because realistically, it's harder to test the bottom end for failures. I mean, you can test end float on crankshafts and all sorts of things. But yeah.
Interestingly, in my drag racing engines, we went through, with my own 4G63, we went through a range of different crankshafts. And at the time, we were probably punching around 1,000 wheel horsepower there or thereabouts and revving the thing to 10,500 RPM pretty regularly. And I'd sort of, every time the engine got pulled down, you'd get the crankshaft crack tested. And we started with, back in the day, what would have probably been a $4,000 or $5,000 billet crankshaft. And this time we had that crack tested, I can't remember how many meetings it had done. It's cracked the fillet radius on a bunch of the journals. So you sort of cry a little bit and throw it in the bin and put in another one, which is obviously an expensive way of going. And at one point I couldn't get the billet crankshaft. So the only thing we could resort to was a factory 4G63 crankshaft from Mitsubishi. And I mean, they're a good item, but they're not made for 1,000 wheel horsepower and 10,500 RPM. And interestingly, I kind of worked out over about 2 or 3 seasons of racing that the 4G63 Mitsubishi factory crankshaft actually lived just as long and just as healthy as these mega dollar billet crankshafts. It'd still crack and I'd throw it away, but I felt a lot happier about throwing away something that I think at the time I was paying maybe $1,200 for instead of $4,000 or $5,000. But the other thing that came from that is, because you don't really know, maybe you pull the engine down at the end of a season of racing and it's done 50 or 80 passes and it's cracked. But did it crack after the 10th pass, or did it crack at the end? I mean, when you see a crack, obviously you can't in good conscience put the thing back in, but that was always something that was in the back of my mind. How long has this been cracked for? And at what point is it actually going to break into 2 pieces? I fortunately never found that out. But sometimes what you don't know doesn't hurt you.
Yeah, that story that you just said was very funny. I'm very close friends with Mick Baghdadi at Mixed Motorsports in Sydney. And I remember being in his workshop one night and looking into an SR20 that he had, dart and sleeve, full to the deck of concrete in the block, billet caps with a factory girdle. And I've looked at it, cast block, and then I've looked at it, and inside it had like alloy rods, pistons in it, and a stock crank. And I looked at it and I said, Mick, are you kidding? I said, you're putting a stock crank in this engine? And he goes, Trevs, the only engines, like all the manufacturers tell you there's a horsepower rating on this billet shaft. He goes, the only manufacturer that doesn't give a horsepower rating is Nissan OEM. And I was just like, are you serious? And he goes, mate, the billet shafts crack all the time. He goes, I've put these OEM shafts in and they don't crack or blow up anywhere near as much as the billets. And I've sort of come to think that maybe that the cast crankshafts actually have a bit of spring, a bit of give in them, and as where the billet shafts are so brittle that they're probably not forgiving when it comes to, say, like tire shake or really heavy, intense shock loads of clutch dropping, things like that, where they're copping this load and they're just cracking there, where versus the cast iron crankshafts are maybe a bit more springy and copping a bit more before they crack. So it's funny because there's a lot of cranks that I've had where I haven't really found the limits to them yet. I'm still pushing factory crankshafts in certain engines, and I'm still not finding limits yet.
And I think there's a mentality as well that I know I've been guilty of falling into, that I'm building this engine and maybe I'm wanting to double the factory power, so therefore I must change every single element inside of the engine. And often that's just simply not the case. I mean, if we roll back sort of 40 or 50 years, the quality of the factory parts wasn't where it is now. The sort of quality control, the materials they had access to, etc. It's all different. So I think what I'd say is quite often a lot of the factory componentry is actually much, much better than we give it credit for. The flip side of that, I'd say, is I guess in the drive to reduce the cost of parts and also reduce the reciprocating weight inside of the engine, rotating weight inside the engine. Conrods, I've seen a lot of factory conrods where you sort of take one look at it and think, if I rev this 500 RPM higher than what it is currently, or we make 20% more power, this thing's going to just bend in half. But that's a pretty simple upgrade path anyway for the conrods. But yeah, I think point of the conversation is don't necessarily think that you have to replace every single component. A little bit more of a thorough analysis and seeing what other people are getting away with is definitely worthwhile. It could end up putting a lot more money back in your pocket as well.
For sure.
All right, let's just talk about the different engine combinations with the 4A. And this is it's quite a large family of engines there. There's the 16 valve and big port and small port variants. There's the supercharged 4A GZE. Then there's the 20 valve and silver top and black top variants. And then there's also the other options where people are using 7A bottom ends, which you kind of alluded to with your earlier boss. So give us a quick tour of that Toyota factory sort of engine combinations and what your sort of go-to options are. What do you prefer?
So again, when it comes to like selection of the engine for the task, if I was looking to build an aspirated engine it already comes with a lot of good parts out of the box where I'm not having to purchase external things like the independent throttle bodies and things like that. Aspirated, I'd definitely go for the 20 valve, silver top and black top. Silver top, if you would only run if you can't get your hands on a black top. Black top's being the best one. Bigger exhaust ports, port dividers on the intake, bigger ports all over, bigger throttle bodies from factory, higher compression ratio, lightweight rods. All these things make a black top so much better of an engine compared to the silver top. Silver top's something you get if you want to do a really hard way to turbocharge an engine, a 4A. If you want to turbocharge one, the small port is probably the best one to do, or the 4A GZE, which I don't think you're probably going to find too many of them around anymore these days. The 4A GZEs are pretty hard to find, I'd assume.
Yeah, I think a lot of this stuff is now getting pretty hard. I mean, it's an old engine as well. I'm interested just to dive into the 20 valve versus the 16 valve for a turbocharged combination. You mentioned that the 20 valve would be a hard way to build a turbo combination. I did that, so I'm interested what you think is harder about that combination.
Okay, so if you were going to turbocharge a 20 valve, the silver top 20 valve is the best one because it has stronger rods. If you look at a black top 20 valve rod versus silver top, you would very quickly laugh at how small the 20 valve blacktop ones are. You'd be surprised that they don't just break looking at them.
Yeah, they look like a twig. It was actually triggered what I was talking about before with the fact a lot of factory con rods, you can tell. You don't have to be an engineer or a metallurgist to sort of have an inkling that maybe doubling the power is not going to be that smart with that particular product.
So going back to Silvertop and turbocharging that, why it would be hard, one of the reasons being the injectors that you need to put into the actual engine to make it work are very hard to find. I think they're 373 cc's of injection standard, and I think there's not a lot of options to get aftermarket injectors. I think the biggest that they do is like an 800 or 700 cc SARD injector. Now, most guys these days are using E85-based fuels, and I don't know how SARDs go with ethanol-based fuels, but personally, that's not a lot of fuel injection for me if I was going to turbocharge. Normally when I turbocharge, I'm going for more than 250 horsepower.
Yeah, those are valid points. So a couple of things I'll add to that, which we could have got into anyway, is when I built my Silvertop 20-valve turbo combination, I did start with the AW11 4A GZE bottom end, so supercharged factory bottom end, and what that gave me over the Silvertop was a much beefier connecting rod. So I had no problems with those rods, and as I mentioned before, I sort of ended up to 500 wheel horsepower, so it was no slouch. The injector issue, I had blocked that from my memory, because you're absolutely right, that is a ball ache. The 20 valve manifold basically incorporates these side feed injectors and the fuel rail as part of that. So you don't have the flexibility of any top feed injector. I think I actually ended up converting it to take a top feed injector, and it was a hell of a lot of work. Obviously, you can get around anything if you put your mind to it, but yeah, I'd completely forgotten that was a challenge.
Also, you've got independent throttle bodies, which you probably also would know if you're just using the factory intake manifold off that cylinder head. Independent throttle bodies plus tuning for turbo, I find a lot harder. I find it easier if you've just got a single throttle body with a big plenum chamber, and then map-based tuning, very, very easy.
So it's interesting you say that. I know that a lot of people really struggle with individual throttle body turbo setups, and I think a lot of that came maybe in the earlier days. There are a couple of factory combos like that, and the Nissan RB26 and the SR20 GTIR are two examples that spring to mind. And I think most people probably tried to apply what they already knew worked from a conventional engine with a plenum and a single throttle body. Map-based tuning, as you mentioned, and we're using that manifold pressure signal as the load axis for our fuel and our ignition tables. Problem is that you don't really get a good signal when you've got individual throttle bodies, even though they'll have a map balance bar, which basically is taking map signal from behind each of the throttle plates and averaging that. It's still not a signal that you can really use as your load input. So I think the game changer there is, as long as you understand that and you run your main fuel table based on throttle position, alpha N, with a background compensation for manifold pressure, that actually works really nicely. And I actually find I incorporate that quite often, even with a conventional single throttle body setup, and it gives really nice control of the fueling under part throttle conditions, which most people don't look at, but I'm kind of a bit of a nerd like that, so I do. So yeah, it needs to be treated with care, I guess, is what we're trying to say here.
Definitely. That's exactly how I tuned my 20 valve blacktop when it was Maatouk M4. It was the alpha N throttle position and then a manifold compensation table, which was funny because I was running over 32 pounds of boost in the car, and my map sensor was a 3-bar, so we actually maxed out the 3-bar, and then rather than just put a cut in, we basically told it to disregard and then added like 20% of fuel trim over the 3-bar map. So we just said, ignore that and just put extra fuel trim in. So that was pretty funny.
Possibly not the nicest and most precise way of getting the results, but sometimes you have to do some odd things to get through.
We were just doing it on the dyno because at the time we actually lifted the cylinder head there. We pulled a thread out of the block, and funnily enough, we're actually incorrect in our timing. There's one of the things you have to watch out for on a 4A is if you actually swap between Silvertop and Blacktop oil pumps and 16 valve timing front covers, a little plastic cover. If you mix and match those, sometimes you're going to have a 10-degree difference between your timing gear on the front and the actual where it points to. So what we were timing on the engine was supposed to be 15 degrees before top dead, was actually 5. So we were actually 10 degrees low in our timing map, and we were putting about 24 degrees of timing in the top end on the laptop, and it was making about 400. It was hard to say because it was wheel spinning on the dyno this is a long time ago, and we had about 6 people in the boot trying to hold this thing down. It was making about 400 horsepower at the tyre at about 28 pounds of boost, and from our experience it should have been making more. So years later I end up sort of going, why did it do that? And I had upgraded to a Haltech Elite at the time. I ended up putting a dial gauge on it, a degree wheel, and finding out that it was 10 degrees wrong. So once I corrected that and then pulled some timing out of the map and then took it for a drive, I think I was probably making more power just by my butt dyno driving around. Felt it was probably making more power on 22, 23 pounds than it ever did on 32 pounds. So 10 degrees will make a bit of a difference.
Yeah, absolutely. I mean, you're at least the safe way. It's always much more dangerous if you're over advanced by 10 degrees and the engine's actually getting more timing than you assume it is. But it is a good point to make, is when you are mixing and matching between different parts from the same manufacturer's parts catalogue, understand that there can be subtle differences in elements such as the timing marks, and that's a pretty important thing. But, if in doubt, you can always make up a true TDC stop and a true TDC marker and actually find top dead center and know exactly where it is. I've done that a few times as well on various engines and found that even the factory timing marks suited to that engine might be out by a couple of degrees. So, they're not always pinpoint accurate. So, there's a lot to learn there. The other element as well with older engines where they run a factory harmonic damper with the 2-piece with a rubber sort of intermediate, and you've got the timing marks on that outer ring. I've seen where that is actually rotated relative to where it's keyed to the crankshaft. So you've got this timing mark that you're trusting your life on, and it's out by 5, 10, whatever degrees, who knows. So
seen that too. Crazy.
Definitely an issue with some of the older engines. I just wanted to take a moment out of our episode here with Matt, and if you are enjoying the episode so far, then I've got a course that I can guarantee you'll also love, which is our Engine Building Fundamentals course. With all of the enthusiasts that we've dealt with over the years, we find that enthusiasts are keen to do just about every part of their project build, but tend to shy away from building the engine, thinking that it's simply a task that's beyond them and that they're going to have to outwork this or outsource this to a performance workshop. The reality is nothing could be further from the truth, and just about any enthusiast who's got a little bit of patience and an eye for detail can build a quality and reliable engine with only a modest selection of tools. Our Engine Building Fundamentals course covers exactly what you need to do. This is a generic course as well. We've obviously been talking about Toyota's 4AGE within this episode, but the skills that you learn building a 4AGE, for example, are also completely applicable to any type of engine. Maybe an LS pushrod V8, a quad cam V12, just about anything in between. It does not matter. You'll learn about the parts of the engine, you'll learn about the clearances and the tolerances inside of the engine, and you'll learn how you may need to adjust those clearances from what the factory recommend for an engine that's maybe going to make twice the power and maybe rev another 1,000 RPM beyond the factory rev limit. You'll learn the machining operations that get applied to the raw materials or raw parts for your engine, and this is going to allow you to speak the same language as the engine machinist, ensuring that you get the right results and you're not paying for operations that aren't essential. If you are interested in learning more about this course, then we're offering a coupon code which is MT Performance 50. You'll find that in the show notes. That'll get you 50% off the purchase of our Engine Building Fundamentals course. Also mention here that even with that coupon code, if you purchase the course and decide it's not quite what you expected, no problem. We offer a 60-day, no questions asked money back guarantee on all of our courses, no exceptions here. So there is zero risk purchasing. All right, let's get back to our interview with Matt now. Coming back to the 16 valve versus 20 valve battle. So if we're talking naturally aspirated, and this is just my take on a number of them that I've tuned for customers, I always sort of found that in 100% stock form, maybe with an intake, headers and exhaust, but nothing else, that the 20 valve and definitely the black top really smashed it out of the park compared to a 16 valve. But conversely, once you start pouring a bit of money into developing the heads, it seemed to me that the 16 valve was a superior choice if you were sort of going all out. Is there anything in that, or is it very much dependent on the specifics of the engine?
Not very much specifics. I mean, the 20 valves definitely do have the potential to do really well. The one thing that does let them down is valve spring. So once you start going on a 20 valve up into the higher duration camshafts, around the 300 degree camshafts or 290 degrees, with the lift that you need to do that duration, you end up finding that they start hitting valve float. So another sort of example is my personal 20 valve. I had 292 degree toe to cams in it, and we're on the dyno putting about 30 pounds of boost in the car, and we found that the power would basically just flatline out. We couldn't figure out why. Eventually, I changed out to a 272 degree Kelford with less lift, a couple of mils less lift, and I ended up putting some spring bases under the springs because I was basically maxed out in my spring max lift with the toters. So once I went back to the Kelfords, I had a few more mils to play with, so I ended up shimming them up about 1.5 mils. And when we put it back on the dyno, I ended up making substantially more horsepower on less boost with the Kelfords. So I believe that I was hitting substantial valve float. When I disassemble an engine, you can actually find valve float in the retainers and the collets. So if you're on the head disassembly bench and releasing them, a good sign of valve float is the keepers will actually be jammed in the retainer, and you actually have to give it like a fair bit of pressure to release it. That's a really, really good indication that you've been sustaining valve float.
Okay. Is this sort of really come down to just an inability? Obviously, we don't have the ability to have an image here on a podcast, but for those who haven't seen a 20 valve head disassembled, I mean, the valve springs are very, very small. Is it just a lack of an ability to get something better that's going to fit the space?
Yes, that's correct. So with a 16 valve, in all cases, the 16 valve has the option for a twin spring, so you can put up to 110 pounds spring pressure on at base height. So you have the option to do shim under bucket, solid conversion, no shims, whereas the 20 valve just doesn't have the same options when it comes to getting the parts involved for it. The 16 valve obviously does have its drawbacks with its port angles, so it's using basically the port comes in dead square and has to make quite a sharp turn into the valve face, as where the 20 valve, the ports are quite raised. So there's differences between both of them in benefits to both. But at the end of the day, if you want to turbocharge a 4A or make a good aspirated one, it depends to what level. The 16 valve is always going to be better to turbo because you can get the spring pressure out of it. Because turbo is obviously where you're going to make your horsepower. The motor just has to hold together for the ride. And then for the 20 valves, up to a certain point, aspirated, the 20 valves are going to beat it. And then once you start pouring absolute stupid money into it, that's when the 16 valve is going to start beating the 20 valve.
Yeah, no, I mean, that pretty much matches exactly what I saw. I mean, a frustrating thing, and it sort of comes back to our earlier conversation about having everything working in harmony with a naturally aspirated engine if you want the results. I did a little bit of development work for a customer who had I think it was a blacktop 20 valve, and we'd started with this thing. It was stock standard, and I tuned it and it made whatever it made. I can't quite remember that.
110 kilowatts or something.
So yeah, nothing to write home about, just middle of the road where it probably should have been. And he then decided he was going to go wild with this thing. So he pulled it all apart and he got the head ported and new cams and basically all of the things that you'd expect you should do. And 12 months later, we got it back on the dyno, and I hate to think how much money he had poured into this thing, and it made 5 more kilowatts or something like that. And
it's so upsetting.
Well, the worst part about it was it made 5 more kilowatts peak and it lost like 15 kilowatts down low. So I mean, the whole thing really just went backwards in an expensive and soul-crushing way. But this, unfortunately, is something that can happen with naturally aspirated engine development if you haven't sort of gone through scientifically and analysed exactly what needs to be done and each part along that path. Coming back to sort of strengths and weaknesses, if you're talking 16 valve, what are the parts that need to be upgraded, and what order would you be sort of going through those parts? And let's talk here about both an NA build and a turbo build.
So naturally aspirated build, I mean, up to a certain point of camshaft lift and duration, you can get away with running the shim over bucket. Because I'm an engine builder, I tend to just get rid of that straight away and run solid. You can buy solid buckets from the wrecking yard out of other engines, other Toyota engines. I think the 1ZZ, they're completely shimless. So if you just go to a picket part where you can pull the parts off yourself, you can just go to a wrecking yard and start pulling buckets out of cylinder heads and then start mix and matching them into your 16 valve until you've got all the right clearances.
Let's just stop there for a moment and just clarify what we're talking about, because these terms that are sort of second nature to you and me, a lot of people won't have heard. So shim on bucket, what's that mean and what is a shim?
So the shim is like what determines the valve lash in a overhead cam engine. So you've got the lobe that runs against what looks like an upside down bucket, and then essentially the shim will sit on top of it inside a castellated section. So the shim then determines the clearance, and then you can get varying size shims to give you more or less clearance. Then you go to shim under bucket, which is essentially like a lash cap style, which again looks like a smaller bucket turned upside down on the valve with a bigger bucket on the top side of it.
A bucket in a bucket.
Yeah.
Again, I wish we had the benefit of some simple drawings here, but hopefully people are picking up what you're putting down. Now, the interesting thing with the shim on bucket, which is a horrible, horrible design, is that, well, you tell us what happens when you start putting a decent cam in there.
Well, basically, once the lift and the duration gets too high, as the lobe starts to come around over the bucket, it will actually spit it out. It will pick the shim up and spit it out into the cylinder head, and it's just catastrophic from there. It is just, imagine a 50-cent coin flying around in your valve train, or a 20-cent coin rather.
Yeah, it's not going to end well. So the common upgrade there was if you wanted to run anything with a reasonable cam profile, you're going to throw the factory shim on bucket system away and go to an under bucket shim. Shim under bucket. So that gives you the ability with these little lash caps, the little bucket that essentially sits on the top of the end of the valve. You can get these in different thicknesses, and that's how you're setting your valve lash or clearance. And then we go one step further and we've got a shimless arrangement. So tell us about that one.
So basically Toyota has other versions of engines, and you can look this up. You just got to jump on Google and have a look. But you'll actually find that Toyota has buckets that have the shim is actually incorporated into the bucket. So the bucket is actually size designated. So if you know what clearance you roughly need to be, let's just say you have a shim over bucket design and you have your clearance set, you can measure the overall thickness of that bucket with, say, a micrometer, which looks like a G-clamp for anyone who doesn't know what they're looking at, a very accurate G-clamp. And you can measure the overall thickness and then order or find the buckets that are shimless, where the bucket is, like I said, determined by its thickness, and then just put that straight into the cylinder head and it works. And you've got no shim arrangement. It's like 40% lighter, so the valve train is now substantially lighter, so you don't need as much spring pressure to operate the valve or return it. So there's benefits all over to that. But again, like you say, the 16 valve, that's the one downside to the 16 valve that the 20 valve has over it. They are a shim under bucket from standard.
Yes, yeah. All right, let's move down a little bit further. What other sort of key parts do we need to consider in terms of strength? I mean, are these engines that are known for head gasket integrity problems, are they known for crankshaft failures or bearing issues? Yeah, what do we need to know?
So when it comes to the 16 valve in general, I mean, I've personally done this plenty of times. We've put turbochargers on them. Disco Potatoes would be an old school turbo that we've done back in the day, and cobbled together turbocharged subs with Microtech ECUs back in the day. And we were running 220 kilowatts in standard 4AGEs, like small ports, big ports, 3 rib, 7 rib, it didn't matter. Like we were just running pretty much anything, and they would run about 220 kilowatts, and we wouldn't really break them. The one thing we would find is you would hurt bearings in them, but that's generally if they have no oil in the sump. So if you keep oil in them, they don't break, generally, at about 220 kilowatts.
Yeah, there is a common belief that as long as you keep oil in a Toyota engine of just about any era, it'll live forever. And there's a lot of truth in that, I think. But
yeah, definitely.
Most engines are going to like oil if they want to survive. A couple more elements that you've just brought up here, which I want to dig into. 3 rib versus 7 rib. So this is referring to the blocks, and no miracle here. We're talking about some vertical ribs that are cast into the block, and the 7 rib has 7, the 3 rib has 3, and it was always sort of said that the 7 rib was way superior in terms of strength to the 3 rib. So any truth in that, or have you found good reliability with either?
So when it comes to the 3 and the 7 rib, the only 4AGs that were 3 rib were the very, very early big ports. Like, I'm talking very early. Now, those particular 4As only had a 40mm crank pin, so their big end journal, or the rod journal on the crankshaft, was 2mm smaller than the later model generation. Now, they also had an 18mm gudgeon pin, so not very common for parts to get pistons or rods for those. So the very early 3 ribs aren't really desirable when it comes to modifying a 4A. Then as soon as you move over to the early big ports that were 7 rib, they've all got the 42mm crank journal and the 20mm gudgeon pin, and those were more desirable for parts.
So what really you're saying there is the 3 rib versus the 7 rib, it's more a case of understanding that also means you've got the bigger crank journal and the bigger wrist pin. So it's not really the block strength, it's the internal component strength that's more important there.
Yeah, pretty much. And like you say, I was talking with Merle Swan, the owner of the former Atlantic car that we're taking to Pikes Peak. He was telling me that the earlier blocks, the earlier 4As, when they were running them in their former Atlantics, the 3 ribs, they were cracking because they're actually a stress member of the actual chassis of the Formula cars. So they said the earlier Formula, the Swifts, so they're a Swift chassis, Swift engineering. Now, they didn't have as much integrity in the chassis, so what was happening is the cars on cornering would actually twist and the block would split. So they moved to the 7 rib blocks, and they were actually putting these little girdle plates between main caps 2 and 4. And that was actually tying the main caps into the side of the block to stop the block twisting and cracking. So I don't know how much. I've never pushed a 3 rib block to a limit to see what it'd actually do if it split, but I haven't really seen 4A blocks blow up, incredibly, like throwing the rods out badly or splitting bores or the actual block splitting on the outside. It's not something that I've actually seen so far. And I've pushed some of these engines to 400, 500, 600 horsepower.
Sure. Okay. The other element that I wanted to dive into there is big port versus small port. And the name probably is pretty indicative of what we're talking about. But what are the differences between these cylinder heads? Which is the superior one to have, and why did Toyota change?
Okay, so it started off with the big port 4AGEs, and they thought that the bigger ports were going to be a benefit to making power. So they incorporated something called TVIS plate, which was basically a set of tiny little throttle bodies in the intake runners to increase airspeed at low RPM. These were shut, and then at 4,500, these little throttle bodies inside the intake runners would actually open up, and then it would increase the airspeed. Toyota then quickly realized, and I think this is probably when fuel was probably getting better in the industry. So I think that after that, what happened is Toyota said, oh, look, we can just increase the compression ratio and remove the TVIS because it's a failure point. It's more moving parts for no reason. They decreased the ports to a small port, which is just a fraction under the size of the big port ports, but they increased the compression ratio, and that ended up netting them more horsepower because I don't think the big ports needed all that port. They also didn't have the compression ratio or the cam to really drive the power. So small ports were the later generation to the big port.
Very similar. There's a lot of parallels there with the 4G63 as well. The early 6-bolt blocks had a very big port head with that same, essentially, Mitsubishi's take on the butterfly arrangement in the inlet runners. And then once they got into the Evos, they went to a way, way smaller port in the head, got rid of that butterfly arrangement. Now, if you're looking at a candidate for a build and you're going to go all out here, is the big port the one to have, or the small port's more than adequate?
The next question I'll ask you, what's your budget?
Okay.
So realistically, look, that is literally the question I have to ask customers. It's, what is your budget? What is the horsepower target? What fuel are you going to be using? And then we can start to create a plan from there for your horsepower goals, because realistically, again, expectation versus reality, we have to be real. If you come to me and say, hey, I want to make a 250 horsepower 4AGE, I'm going to say, you understand that that's going to be really rough to drive on the street. you're going to need something with a dog engagement gearbox because the thing needs to rev to 10,000 RPM to be efficient in its power creation. So a synchro box will not shift to 10,000 RPM. I can tell you that right now. So you need a dog box gear engagement. You need a fuel that can cope. So E85 is such a thing nowadays. That's not a problem. But you need the gearbox. The car's not going to drive very nice under that. So their expectations are like, oh, I'm going to make 250 horsepower and it's just going to be weapon to drive. But that's not really the case.
Much.
Yeah.
Yeah, I think until you've actually experienced living with something that is that aggressive on the street, you don't actually know what you're getting yourself in for. I'm glad you actually mentioned that point about the dog engagement gearbox, because I don't think too many people appreciate that a synchro mesh gearbox, a stock OE style production gearbox, often won't shift at these sort of RPM ranges, and people just don't appreciate that that's an issue. So obviously there's a variety of other benefits that come with a dog engagement gearbox, including the selection of closer ratios that work with what will be an incredibly narrow power band. But yeah, I mean, having the gearbox be able to actually shift gears at 10,500 RPM, obviously that's kind of a benefit as well. All right, so in terms of that, obviously no clear winner there. There's a lot more that goes into deciding which way to go to, and obviously that's something you can have the conversation with the customer at the time. Capacity, though, let's talk about that, because the 4AGE being only 1.6 litres in capacity, the old story, there's no replacement for displacement. I'd argue turbochargers do a pretty good job of that, but if we're staying naturally aspirated, there's definitely some truth there. What are our options for getting some more capacity into these little engines?
So now we're talking. So when you asked me before, I want, this sort of horsepower out of a 4A, I would basically turn around and say, hey, look, two easy factors. One, 4As are getting harder to find. And if you find one, generally they're going to have damage to the bottom end, like a big end bearing damage or, some sort of bottom end damage. If the cylinder head's savable, go do yourself a favor and buy yourself a 7A FE, because now we're talking 1.8 litre capacity and the opportunity to go even bigger again, up to 2 litres. So, I mean, the 4AG cylinder head flows pretty well. So with a set of camshafts and a set of springs, rods and pistons in a 7AFE bottom end, and generally the 7AFE bottom ends were owned by grandmas who just go down to the shops, once a week. And there's so many of them. So go do yourself a favor, go buy a 7AFE bottom end for about $400 from the wrecker. Go get a 4AG head from somewhere and put it together and you'll have a good time. I've got a customer's A86 that does about 180 horsepower at the rear tyre. And it does that. It's all in. It's all in at 180 horsepower by like 8,400 RPM. So his synchro mesh gearbox manages to change gears. And it wasn't too much of an expense to get it to that level.
Okay. When you're looking at one of these 7A combinations, what are the parts that need to be changed out in that bottom end? Are you straight away, you're just basically retaining the crankshaft for the stroke and the block obviously itself? Am I right in assuming that a set of aftermarket pistons and rods is going to be an essential, if for no other reason, to get the compression ratio where we want it for that combination?
Yeah, so with the rods and pistons in them, the rods that come out of them, again, very comically weak looking. I've seen guys actually run them before and they have had good success with them. But by the time you spend the money taking them to a machinist and getting them removed, getting a floating pin conversion done on them, so bushing the little end, so you can put a late model, you need to put a 4A GE piston in it because obviously the valve reliefs are different, the compression ratio is wrong. So you can literally, if you're running a small port cylinder head, you can go buy small port pistons, put those on a 7A rod into a 7A FE bottom end, and it will bolt together and be fine.
Okay. The reality is converting those factory rods to suit, it's almost a coin toss. You might as well just buy an aftermarket component that's going to be stronger for just a little bit more money.
Yep, the forged rod, by the time you spend the money on a forged rod, you've got ARP bolts, they've got the floating conversion done, they're already a forged rod, and you're probably only 20% extra in money to get them from the factory ones converted over to a floating pin, put ARP bolts in them, and then re-enclose and hone the rods. To prep the rods, essentially, you spend 20% more, you get a forged rod.
Yeah, it makes sense. And I mean, I'd sort of put that almost down to cheap insurance as well. Having a known rod that you're just within reason not going to be able to break, it makes a lot of sense. When one goes out the side of a block, it's kind of like the same situation when you drop a valve. Not a lot of usable parts are going to be left from that engine. What about the integrity, reliability, strength of the factory Toyota 7A crankshaft? Does this sort of fall back into that conversation we were having previously where factory components often are a lot stronger than people give credit for? Or is there a limit to those?
So one of the things that I've found with the 7As is harmonics. The weight of the conrod, obviously the weight of the conrod and the piston in its reciprocating mass wasn't designed to work with a forged rod and piston. So once you go from a factory 7A conrod and piston, the mass is so much heavier going to a forged component, a forged rod and piston. So what I find is the center of the crankshaft actually does this over-exaggerated. What I'm doing with my hands is basically saying that it moves up and down. So what I find is the center main bearing actually gets flogged out very early on with sustained high RPM. If you cap the RPM at, say, 8,000, they don't seem to have an issue. But if you start revving them over 8,000, the center main journal bearing starts to get flogged out.
Okay, interesting. Definitely something to look at. We'll keep an eye on there. Lastly, with the block, any reliability concerns there? Another point that we haven't talked about is under-piston oil squirters, quite common on a performance-oriented engine, less so on a garden variety engine. Everyone's got their own sort of ideas as to whether it's worth machining a non-oil squirter block to take oil squirters. Yeah, what's your take on all of this?
So oil squirters, I've had, going away from the 4AGE and just looking at, say, a 2JZ, I've had a 2JZ that was turbocharged, making 800 horsepower in a drift car, had a oil pump failure. The harmonic damper hadn't been serviced in a long time. The harmonic damper failed, pump gears locked up the motor when the oil pump exploded. We pulled that engine apart and it had oil squirters. We damaged the crank and the block. Everything was damaged. So we ended up getting an aspirated short motor. Now we converted that over to a turbo pump and things like that. Now the aspirator didn't have oil squirters. We'd done the same setup with forged rods and we put it together as an engine. 800 horsepower again. Running E85, we found no substantial difference in the teardown of the components like pistons and rods and ball clearance and wear without oil squirters. And I think the oil squirters are a good idea, but realistically, I'd rather have oil pressure up at my big end bearings and let the oil spraying from between the big end, the rod, up into the bores, lubricate everything. I believe under piston crown cooling isn't really necessary on an alcohol-based fuel engine. There's just not the same heat there.
Yeah, I 100% agree with that. As I kind of mentioned, everyone's got their own take on this. There'll be as many people advocating that they're an absolute must and never build an engine without them as people who have successfully been building engines without them. So very much the jury's out on it. But I do take what you're saying there. If you're using under-piston oil squirters, some of the volume of the oil pump is moving is obviously no longer making it to the bearings. And that's really where we want to make sure we've got a good supply of oil. So obviously there's a lot of aspects that go into that as well.
Exactly. It's too hard to say what's best in whatever scenario. I mean, there's two places I like my oil. One is at my bearings and the other one's in the sump. So one of the things that I also see with people that do 4As and even other engines is they overpressure the pump. So they put shims under the oil pressure relief valve. And if you can consider the fact that if you overpressurize the pump, what's happening is the oil isn't actually going into the block. So it's going into the oiling system rather than being dumped back down into the sump. So although you're lifting your pressure, you're also lifting your volume. So if you can consider the fact that your oil is now hung up inside the engine and there's nothing in the sump, you're more likely to cavitate and suck up air from the base of the sump if it's hung up. My theory is, and I've done this with pretty much every engine I build, is everyone else's standards, I might under-pressure my oil systems, but I've never had a bearing failure. So the rules of thumb that you use are the same rules of thumb that I use. Spring pressure per diameter of head, oil pressure, how many pounds of pressure per RPM. That's all definitely valid. I can concur to that.
Yeah. I mean, I think the old 10 psi per 1,000 RPM has always been a good guide, but it's obviously much more important that you're controlling the oil around the oil pickup and it's never going to be sucking up air, because if it does that, it's going to very quickly destroy your engine, no matter what quality oil you're running. I'm just interested as well, just coming back to the 7A combination. So that's going to get you out to 1.8 litres, as you already mentioned. What's involved in the 2 litre sort of A series combo? What would you have to do to get out to 2 litres?
So generally an offset ground crankshaft. So you can offset grind the 7A crankshaft down to a 4A journal size, which is the 42mm big end journal size, which gives you another few millimeters of stroke. And then obviously if you move the piston out to 81.5 or 82 mils, that can basically get you at about 1.930 cc's, 1.950 cc's. There is also billet crankshaft options from a company in New Zealand as well. He offers billet crankshafts and forged rods and pistons to make the 2-litre combinations.
With that offset grinding of the crankshaft, again, no images to go along with this, but basically what we're doing is offsetting the center of the conrod journal and making it smaller in diameter so that we're getting a net gain in our stroke. It's a terrible way of explaining it, but hopefully people are picking up what we're putting down here.
It's a difficult one without drawings, isn't it?
Yeah, the angle I'm going with here, I've never actually gone down that path myself, but I'm just wondering what you've sort of seen in terms of reliability. Generally, these factory crankshafts are induction hardened, so they've got a hardened surface that might only be, I don't know, maybe 5 or 10 thou deep or something of that nature. So obviously, as soon as you offset grind the journal, you've ground through that. Is it essential to re-harden the crankshaft? Do you nitriding it after that process to reintroduce that hardened surface? Or, what's essential?
So the Toyota 4AG and 7A FE, their crankshafts aren't hardened. They're soft. So essentially, the 7A offset grinding of the crankshaft, you can do it with no failure issues. Back in the day, my old mentor, Adam Moore, he was running offset ground crankshafts with an Argo rod combination. Argo's a company here in Australia, and a Wiseco piston option. And they were doing that like 20-something years ago, offset grinding crankshafts with a custom rod and piston combo. And they were running 240, 250 horsepower with 8,600 RPM on these 2-litre 4A strokers. They were 1.999 cc, so literally 2 litres. These were in like PRB Clubmans.
Yeah, sure. All right, interesting. Let's move on, and I'm interested if you could give us a bit of a rundown. This is sort of a question we get asked about, and it's also, I think, an assumption that home enthusiasts who want to get into building their own engines are worried about. And what I'm talking about here is the investment in tools that we're going to need to make. I think that the misconception is that in order to build your own engines at home, you need $50,000 or $100,000 invested in tools. And clearly, if we're talking about machining our own components as well, then that's very light. But when we're dealing with an engine machinist, that straight away takes out of the requirements of all of the expensive machining equipment. So assuming also for the average enthusiast who's already working on their car and already has your average mechanic's tool set. So I'm talking here pry bars, sockets, spanners, all of that sort of stuff. What over and above that do we need to start building engines?
I've got one drawer in my toolbox, I reckon. One drawer is enough. So micrometers, you talk 0 to 1, 1 to 2, 2 to 3, 3 to 4. A couple of sets of feeler gauges, one with a 45-degree curl on it and the straight set of feeler gauges, dial gauge and a magnetic post, a ring file. Like there's inside micrometer. I use a pen style inside micrometer. Now, I've done some YouTube videos on this, but when I use the inside micrometers, I don't use that as reference to size. I actually always use an outside micrometer over the inside micrometer to reference for size. But in saying that, literally one drawer of my toolbox is basically dedicated to the measurement process of an engine, and it's enough to get away with that I can build some pretty impressive engines.
Yeah, and I think that's pretty much matches what I've got access to as well. I mean, really, there's not a lot of specialist equipment necessary, except when it gets into precision measurement. Dial bore gauge as well would probably be another one that I rely on pretty heavily. And then, of course, the ring file. And I think that's a place that you do want to spend money and get a good product. I've used some pretty average ring files in the past, and the manual ring file, which you sit in a vise and you can probably pick them up for $30 or $40 US. They're cheap and they'll get you through. I mean, if you want to build one engine, then have at it. But if you're thinking that you might build a few, you'll be thankful that you bought a proper electric ring file pretty quickly after you've filed your second ring, I think.
You're going to hate me because I have that $30 ring file in the shed.
Well, I mean, case in point, it does absolutely work. But yeah, I must admit I moved on from that a fair few years ago, and every time I use an electric ring file, I feel pretty chuffed with myself. And I think the other thing about it is this: you can absolutely do a great job with the manual ring file, but the time it takes and the skill to get the consistency and repeatability across a full set of rings, it's up a notch. So all power to you if you're still using one of those.
You're talking my language. It's one of my most hated tasks of building an engine is filing rings. I hate doing it, but I have to do it, so it's something I have to do, but I really don't like doing it.
All right, so hopefully what we got across there is like you're not going to have to spend thousands upon thousands of dollars for this equipment. The other thing I'd say with the micrometer or precision measuring equipment in general, and yeah, I mean, if you want to get deep into engine building, it's a non-negotiable. You definitely need to have that sort of equipment on hand. There is a risk as well, though, that to the uninitiated, there is a technique that goes into using a micrometer and getting an accurate reading. So if you don't know what you're doing with this precision measuring equipment, you're going to be kind of garbage in, garbage out. And I actually still use plastic gauge as well for checking my clearances. And I know this is a product that a lot of people just do not feel that you can get decent results with, but I've back-to-backed between plastic gauge and using a dial bore gauge and a micrometer, and I still find it to be an absolutely valid technique. What's your take on plastic gauge?
Yeah, definitely. I've had the same results. So I can measure a crankshaft diameter, bolt down a rod onto a crankshaft journal with plastic gauge, and confirm my measurements back to back, and it's within tenths, it's within hundredths, of thousands. So it is accurate. I mean, realistically, and you've probably seen this yourself, mate, I've seen some absolute engines being slapped together and run and work. Like that RB that you were talking about before that had the different rod in it, I was really holding my breath before, but I've done it myself. We put together this RB at Maatouk's one year, and it had 3 different brands of rods in it and 4 different brands of pistons. And mate, it ran 880 horsepower, and it ended up running 8.8 on the quarter mile. And someone wanted to buy the car, and Anthony said, "We're not selling it with that engine in it. Pull it out and build it properly." It was literally spare parts from around the workshop.
And I mean, what you can do for your own project car with full knowledge of that is one thing. What you are going to do for a customer, and credit to Anthony for pulling the pin on selling it like that, it's 2 very different things.
Oh, yeah. But yeah, it was absurd how well this car ran with junk. Like I was pulling bearings out of the bin from other engines that had blown up and piecing together the best bearings out of the worst blow-ups and going, oh, yeah, that'll work. Okay, we'll try that. And unbelievable. I think that engine cost us a total of $3,500 to put together, including the turbo, single cam RB30, made 880 horsepower. You wouldn't believe it, eh? Unbelievable.
Yeah, I'm not that lucky though. If I ever tried to do that, the thing would probably blow up on the way to the dyno. So
it would be my experience too, but it wasn't my car, so that's why it probably worked. It was Anthony's car. He just seems to get away with a lot of stuff like that.
All right, Matthew, I think we'll move towards wrapping this up, and I want to respect your time here. We do appreciate how deep we've already gone into the world of 4As. We've got the same 3 questions we like to ask all of our guests at the end, and the first of those is what's next in the future for you? And let's actually dive into this as part of this question, because we haven't really talked about the fact that MT Performance Engines, your business at the moment, is sort of a side hustle as well, isn't it? So what's the development path? Are you looking at making this business a full-time gig, or are you quite happy with continuing to develop it as a side hustle?
It depends. I'm flying by the seat of my pants here. I don't know what I'm doing. I'm just literally out here doing my thing. And put it this way, if the opportunity comes around that I can expand, I will. If it doesn't, I mean, it's like you say, it is a side hustle. It's not my day job. I just enjoy building engines. I enjoy tuning. I enjoy racing. I love it all. So I'm just going to keep going with the flow, I guess. There's no real plan that I have with targets. And it's sort of just, if the right opportunity comes along, I'll go with it and just keep moving forwards.
Fair. On that note, what's the main hustle? Is that in the car industry as well?
No, I'm a marine engineer. So I actually work on ships as an engineer in Sydney Harbour. Yeah, so...
Quite different.
Yeah, different. I basically look at gauges all day and drink coffee.
Could be worse. All right, next question, Matt. Is there any advice you'd give to a younger version of yourself, or maybe one of our listeners, to help fast track the career path you've gone down, maybe avoid some pitfalls that you've come across?
I can give them some advice on what I done when I was younger. Go to wrecking yards and strip engines. Figure out how they work, because that's what I done when I was about 17 and I got my license. I drove out to the pick apart wrecking yards where you pull all your own parts off, and I would spend a whole day there stripping engines, and I wouldn't take anything. I would just walk out of there and they'd go,
free education.
Mate, and the things that you would learn all sorts of things. How does this engine do this? Why do they have this? And I was just curious kid. So stripping engines all day long and then going home black and exhausted and just going, I'll learn a bit there. And the first engine I ever built was a success because of what I learned tearing other engines apart.
Yeah, okay, interesting. Just sort of to cycle back to our conversation about tuning, I didn't quite touch on this, and the conversation about the fact that you don't have to break a bunch of engines to learn how to tune, which I absolutely stand by. And I think advice to anyone who wants to get involved in that and start developing the skills of tuning, these days it's very easy to, there's probably more turbocharged engines that people are interested in developing. And obviously, as we've touched on, you can make great power out of a turbocharged engine. It is absolutely possible to start learning how to tune on an 800 horsepower turbocharged engine, but your sort of operating envelope and your room for error is very different. So something naturally aspirated, 4AGE or something of that nature, it's still possible to break them, but your operating envelope is much, much wider. And it's definitely a safer place to get started, get stuck in and learn those skills. And once you're comfortable with that, it becomes easier to step up the power levels and add a turbocharger and still feel confident in tuning. So I just wanted to add that in there as well.
Definitely. Understanding the fundamentals of how an engine actually operates is probably the key thing. A lot of tuners these days are just kids with laptops, but they're tuning and they're getting a result from numbers they're inputting into an ECU, but they're not understanding what the engine is actually doing. And that's one of the things that I've seen. If I change a number, my AFR target does this. That's what I want it to do. But what is it actually? What do those numbers mean? That's the question. And a lot of these guys won't know that. What do these ignition figures actually mean? I've talked to tuners who don't even understand what the duration of a camshaft means. And I've just gone, how do you tune engines and not know what the numbers mean on a camshaft?
Unfortunately, all too common. But yes, having that deeper fundamental understanding, irrespective of whether we're building engines, whether we're a mechanic, whether we're tuning, I think that always allows you to do a better job rather than just, I get this car in, I put these numbers into the fuel map and these numbers into the ignition map. I don't understand what they mean or why I'm doing it, but this is what I have to do to get the result I want on the dyno and onto the next car. That's not a tuner, at least in my opinion anyway. All right, last question for today, Matt. If people want to follow you and see what you're up to, how are they best to do so?
Look onto Facebook, MT Performance Engines, Instagram, same thing. I'm mainly more on Instagram. If they want to follow videos that I've done on YouTube, I work with a YouTuber called Nico. His YouTube channel is 199 Nico, Niko 199. And you can follow along with the builds that I've done on there. His personal Sprinter, the former Atlantic engine. I've got my own personal race car on there. And we've got heaps more content coming up, including me and him will be going over to Colorado this year for the Pikes Peak Hill Climb event for the former Atlantic turbo car that we've just done. Yeah, so follow along for that if you want to see what we can do.
All right, we'll put links to all of those accounts in the show notes to make it nice and easy for people to find. All right, well, it's been great chatting, Matt. And I'm pretty sure I can say I've learned a bunch more about 4AGEs that I didn't know before we started. So hopefully everyone else has too. Thanks again for your time and thanks for joining us today.
Thank you very much, Andre. It's been a pleasure.
If you have enjoyed this episode of Tuned In with Matt, we'd love it if you could drop a review on your chosen podcasting platform. These reviews really help us to grow our audience, and that in turn helps us to continue to get more high quality guests. To say thanks, each week we'll be picking a random reviewer and sending them out an HPA t-shirt free of charge anywhere in the world. This is also a great place to ask any questions you might have too, and I'll do my best to answer them if your review gets picked. So this week, a big shout out to Stuart Emmett from the United Kingdom, who has said, great podcast, thoroughly enjoyed the 1.5 hours with Micah from Red Bull Powertrains this week, another in a long line of brilliant guests. Every week there's something that I could take away from the pod, whether it be validating something that I already do or introducing a new view or topic. Andre is a great host and you can sense his enjoyment throughout the interview. Great work. Keep it up. Oh, thanks for your kind words there, Stuart. Great that you are enjoying the podcast. And if you get in touch with your t-shirt size and shipping details, we'll get a fresh tee shipped straight out to you. All right, that concludes our interview. And before we sign off, I just wanted to mention for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis and race driver education. Now remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.